Welcome back, dear students, to the tetrahedron chemistry classes. So in today's class, I am going to solve yet another problem from the spectroscopy book by Pavia and Csir, and this is the problem number 21 of chapter 3, which is given in the exercise, and it's quite a simple problem and elementary problem. It will not take too much of the time. So first of all, what we will do, we'll read the question. So see, the title should not be your combined spectral problem, because this problem is purely based on the proton NMR spectrum. Okay, but since I am dealing with the combined spectral problem, so I have decided to put this particular problem in this section. So I have given this name, combined spectral problem. Okay, the two isomeric carboxylic acids that give the following NMR spectra 1 and 2, both having the formula C3H5ClO2. Draw their structures, most probable structure. The only thing given in the question is the C3H5 and your ClO2, and it is already given in the question that this compound is carboxylic. These compounds are carboxylic acids. So that means one thing is sure, both are having COOH group, this functionality, COOH. This is offset 1.7 picometer, ppm, parts per million. Okay, so this NMR scale is extending from 0 to 10 ppm, and this peak, which is offset by 1.7 ppm, that means it is resonating at 11.7 ppm, and you know, in the range of the 10 to 12. Please remember, in the range of the 10 to 12 parts per million, you always have signal of the hydrogen which is connected with the COO. Okay, so it is quite clear. This is your 11.7, right, for compound A. And in the next isomer, the peak is offset by 2.2. Again, the scale is extended from 0 to 10 ppm, and it is offset by 2.2 ppm. That means the second compound is giving this peak for this hydrogen at 12.2 parts per million. Okay, this thing is quite clear. Now, if you see this particular first spectrum, two triplets are given here and nothing is there in the spectrum, only two triplets here for the compound A. So how we can get the two triplets? This I have already told you. When your CH2 is connected with the CH2, so this will produce a triplet, and this will also produce a triplet. And for the beginners who are watching this video for the first time, the splitting pattern is n plus 1. That means if you want to decide the splitting pattern of these two hydrogen, you need to check the presence of the hydrogen in the vicinal carbon. So this carbon, the carbon is the vicinal carbon, and it is having two hydrogen. To check the splitting pattern of this CH2, we need to identify these two hydrogen as N. So you can write 2 here, 2 plus 1, that is 3. 3, it stands for the triplet, that's why this triplet is here. And same is true for this one as well. Trying to identify the splitting of these two hydrogens, so you need to check the hydrogens present on the vicinal carbon. The number is 2 again. You have confirmed the presence of COOH, and you have confirmed the CH2, and your formula is nothing but, so if you connect these two fragments, this is fragment number 1, this is fragment number 2. If you connect these two fragments, you are having CH2, COOH. This will give you a singlet at 11.7 ppm. This will produce a triplet, and this will also produce a triplet. Okay, now you left with the chlorine. The only possible way is to put chlorine here. There is no other way. Now you need to decide the chemical shift of these. So here you can see, if I go back, this triplet is a little bit downfield, and this triplet is little bit upfield, and you need to decide which one is the upfield and which one is the downfield signal. This is somewhere at 3.8 ppm, right? Downfield signal is at 3.8 ppm. 3.8 ppm of chemical shift to this one. Okay, and for this one I can give 2.8 ppm. So these two signals are there, 3.8 and 2.8. So this is looking like the more correct structure for the compound A. The only question is that this chlorine actually, which is electronegative and as well as the electron pushing. So its electronegativity dominates and it will suck the electron density towards itself, making these hydrogens de-shielded. And you know, de-shielded hydrogens appears downfield. Downfield means higher value in ppm for the chemical shift. So this is your first compound. Okay, and now you can go for the second compound. This is a doublet here and a quartet. Doublet and quartet and one COH group. So acid is confirmed, one doublet is confirmed, and another quartet is confirmed. Only possible way to get the doublet and the quartet is this particular kind of the bonding. Okay. So this will produce a doublet, which is this one, and this will produce a quartet, which is this one. Now you know, if you want to decide the splitting pattern of these three hydrogens, you need to check the hydrogens on the vicinal carbon. This is vicinal carbon having only one hydrogen. If you apply the n plus 1 rule, so you will put n plus 1 here. So 1 plus 1 equals to 2, and 2 means doublet. That's why this doublet is here. And if you are deciding the splitting pattern of this hydrogen, you need to check the hydrogens present on the vicinal carbon, which are 3 in this case. So if you apply the n plus 1 rule, n plus 1, that will give you 3 plus 1, that is 4. 4 means quartet. Okay. So this quartet is there. So you are having the fragments COOH and another fragment is CH and then CH3. The only way by which you can attach a chlorine to the system is on the second carbon. So this is the most probable structure. And now you can see here, this particular signal, this will appear somewhere 12.2 ppm. So if I go back, why this signal is actually at 12.2 ppm, while for the earlier one, the signal was around at 11.7 ppm. So the reason is quite obvious. This hydrogen is connected with the carbon which is having the chlorine. So this chlorine will also de-shield this particular hydrogen, and due to the de-shielding, it will appear little more downfield at 12.2 ppm, while in the earlier case, the chlorine is on the second carbon. It is far away from this particular hydrogen, so de-shielding effect is low. That's why it was appearing at 11.7 ppm. But in this present problem, it is on the second carbon. It de-shield this hydrogen, so that's why it will appear on the 12.2 ppm. Now the chemical shift for this particular hydrogen, it is only one hydrogen connected with the electron withdrawing chlorine. So this quartet will be quite downfield. So I'm writing Q this one, and this Q will appear somewhere around at 4.2 ppm. Go back and check the value. Yes, you can see here this quartet is appearing exactly at the position I have given here, 4.2 ppm, and your next signal, which is nothing but a doublet, I'm adding D for this one. It is appearing at 1.8 ppm. Okay, so this is how your proton NMR spectrum is useful in differentiating the two different isomers. So if you understood the lecture, please like it and do share with your friends as well, right? And if you're watching this video for the first time, please subscribe the tetrahedron chemistry classes. That's it for today. Thank you. Thank you very much.